Okay, thanks everyone for coming. We should go ahead and get started. It's indeed a pleasure to host Éva Tardos for our first visit to University of Melbourne. This, I think, is the first, and I hope there will be more. I know many of our students know Éva through her wonderful book with John Feinberg on algorithm design. But I also wanted to mention a few other highlights of her career. She is a member of both the National Academy of Engineering and Sciences. She received the Packard Fellowship, the Sloan Fellowship, the Guggenheim Fellowship, the Fulkerson Prize, the Danzig Prize, and the Gödel Prize. Éva started off by doing pioneering work in the area of network flows, and since then has done pioneering work in a number of areas, including approximation algorithms, clustering, and much more recently in algorithmic game theory. So we're honored and fortunate to have her visit here. Without further ado, thank you.
Thank you very much, Jackson. And thank you all for turning up, and I hope I have something interesting to offer you, if not along the algorithm. So I want to combine two things in these talks, is game theory and learning. And I guess as the first part of the time suggests, I want to think about learning as a behavior in certain repeated games. And let me start with, actually there's a bunch of co-authors here, maybe nice to point out two of them who are still students. Doris is my student, and Dylan Foster is a machine learning student, and they both might be on the job market next year. So, in case the faculty are interested in, some recruiting opportunity, these are great people. So the kind of games I want to think about is games that we or someone plays very, very repeatedly, lots and lots of times, is the property that an individual action in this individual game won't matter much, but overall they matter a lot. And I think packet routing is one of those. So if, the routers have to decide which way to send packets, but one individual packet is not that big a deal, because if it went wrong, you just drop it and send it again. Of course, overall, how fast you can get the packets across, that's what your experience depends on, so it does matter. I want to think of this as a game, and it's a game because my objective, or my computer's or the router's objective, is to try to get these particular packets across as fast as possible. But at the same time, while you do this, you create congestion, and that hurts other packets who might want to share the same directions or same routers, and you slow down other packets. So you have a direct effect on other people due to the congestion. This model can be thought of as model of graphs and driving, or cars and driving, or packets and the internet. The same sort of thing applies. An individual car just wants to get to its destination fast, but unfortunately, as a side effect, it's slowing down all the other cars. And the way and this is the second word in my title, dynamic population, the way I want to think about it, I want to explicitly think about the fact that traffic patterns, like download patterns, change over time. Like if I read the New York Times, I'm not going to read the New York Times for the rest of my life. I will at some point switch to some other activity. So the rest of you will. And different, and also maybe a classical killer application for the whole algorithmic game theory area was advertising auctions. So as you all know, almost everything you do on the web is monetized via selling ads, which are sold on auctions. That also is an application of the very same story. A particular advertiser for a particular ad pays in a fraction of cents usually, and usually the income from showing a single ad to a single person is nothing. However, this is what monetizes the whole industry. So the same story applies. An individual action, an individual event is not very valuable, but overall, it is very valuable. Now, why do, and again, things change. As something changes in the real world, something becomes popular or unpopular, so the values of this ad change. So again, there's somewhat changing system. For both application, and maybe you should keep this in mind while I try to introduce the more formal model, the speed at which the repeats occur is much, much, much faster than the speed at which the changes occur. Like, if I read the New York Times, I'm going to read an article, or maybe even just the headlines. That will take me a while. Meanwhile, there are many, many, many package code routing. The same thing on ad auction. These sort of changes in popularity may be happening on the scale of a day, or maybe fractions of days, but the ads happen in fractions of seconds. So what's the model I want to think about? So I think of a repeated game, and you can, in many of the examples, maybe it's better to think of delay in packet routing, but equally applies to options. Repeated game, there's a bunch of players, so in this case, the routers. They're routing packets. Say each of them makes a decision. I'm going to code a decision A as action, AI as for personalized action, and then something happens, and then they repeat it again, and then something else happens, and so on. And each of them, there's something happens, and they watch what's happening. You can think about what exactly is the actual feedback they're getting and how they decide what to write. But there are two important things I want to think about, want to actually claim for this talk. One is the applications I'm thinking of, the objective is something averaged over time. Like in the packet question, they want to, on average, spend the packets as fast as possible. So average delay or average cost of a packet. In the auction question, on average, they should make a lot of money. On average, they should show the right ads that are very valuable and not pay much for them. And on this application, I want to think about players who want to learn from past data. That is, whose goal in life, who's thinking, the feedback is what happened to the ads, they get some sort of feedback of that sort, and they want to take what happened in the ads earlier in the day and make conclusions about what they should do later in the day. I think this is a natural attitude for a computer scientist. After all, machine learning is one of the hot things that's happening in our world. And generally, it's very natural in these domains. Routers certainly don't have access to who else is routing packets somewhere else, but they do get routed peak times, so they get information about how good their packets get across. And similarly, in the ad space, both Google, Microsoft, and all the companies are reasonably good in feeding you information about your bid and what you would have gotten, and hey, your bid was way too low, had you bid this higher number, you would have gotten something good. But you don't get feedback on exactly who all is advertising, and definitely don't have feedback on what the hell those guys are thinking. So this is sort of learning from what happened in the past is a natural model of what's the information available to these people, and they're going to have to learn from it. It's also very natural, and this is why I like things that are repeated games of this form, given that the stakes on an individual instance of the game are really low on both applications. Explore, exploit is fine. You can explore. It doesn't cost so much, and you will have ample opportunity to exploit after you learn something. So this is the model I want to think about, and what I want to ask is two very related questions. Can I say something good on what will happen in a setup in a game like this if everyone's learning? You're hoping that if everyone's learning, something good will happen, like overall the system will perform well. And if you have an answer to this question, you definitely want to ask, how much churn can I tolerate in the system and still say that it's it? So remember, I wanted to think about this dynamically changing word. I wanted to think about the dynamically changing word, but not changing that fast. So I want to ask, how fast is it allowed to change? And I still can say something good. This is a very natural question to ask because, first of all, if things is incredibly changeable, then yesterday's experience has nothing to do with today, so good luck in learning. At the same time, if people stay in the system long enough, then hopefully, despite the churn, you can learn something new. And it's a nice way to measure of how small they have to stay. So to get you sort of started on what kind of results I want to think about, I maybe wanted to start by talking about something that's maybe my classical work or my old work in this area is the traffic routing space. And I guess there is this theorem I had at this point more than 15 years ago, this kindergarten about traffic routing. So traffic routing, remember, there was the packets and congestion causing delays. And our theorem said that if you let people route in arbitrary ways that they want to route their packets, that's not not going to be optimal, unfortunately, and this can be helped. But if you design your network so as to tolerate twice as much traffic than what you have, then you can let them route whichever way they want, and overall the average delay is no worse than the optimum would be, socially designed optimum would have been. I think this is a really, really nice message for the internet, because even before we ever proved the theorem, this is what the internet people have been doing. That is, when they see congestion and they see unacceptable delays, rather than telling the packets which way to go, which is probably not viable for other reasons, it's too complicated, just putting more pipes over them. That's precisely what we're telling them. If you have enough pipes to tolerate a higher rate of traffic than what you're planning, what you're going to end up having, then letting everyone just try to route on the shortest path, and yes, they conflict with each other, it's not going to be a big deal, you're going to tolerate enough traffic. So that's the kind of theorem I'm coming from, and that's what I want to say is that that was about a Nash equilibrium. I'll come back again to define what a Nash equilibrium is, but hopefully with the, among other things, the Nash movie, and many of you might have seen Nash equilibrium, I hope. This is about a Nash equilibrium, and one thing I'm sure you all realize that neither of those repeated game situations are at Nash equilibrium. But if you're not yet convinced, I'll show you data to show that no, this is not a Nash equilibrium. This theorem was about a stable equilibrium. So the key notion that I'm going to use is this price of energy. So price of energy in those days was defined the cost of a Nash equilibrium, so total delay in a sum of delays on the Nash equilibrium divided by the optimal social cost. And this is, as the year shows, a somewhat old, actually originally defined by Papadimitriou and Koutsoupias in a paper in '99. So more like close to 20 years old at this point. And in the last 20 years, there have been beautiful theorems repeating this, not just for this one example, but many, many of them. So I guess here are a couple of them, and again, I'll come back to this. Lots of them are about traffic routing, depending on how you model the congestion cost, like we all assuming that the amount to time to get across an edge, of course, will grow with the congestion. You know, more cars than red, the slower you get across. We all know that. The question is, how do I model mathematically that function? And there are different price of energy results. And there's also lots and lots of results in auctions. So auctions are you bidding for something such as displaying your ad or whatever you're bidding for, something will happen in the auction. Maybe the natural things is what usually called first price or second price. That is either you have to pay your bid. You say I'm willing to pay $7, I'm going to cash it, take $7. There is generalized second price and all kinds of classical auctions. There are weird auctions called all pay, where you pay whether or not I actually selected you as a winner, and all kinds of other things, including fair sharing and lots of things here. All have price of energy results. I guess one nice thing to notice here that these numbers are not horrendous. So the price, I'm a theoretician, and I want these numbers to be constant. I want it to be the case that as the system gets bigger and there are more and more users around, the price of energy doesn't go to, doesn't grow with the size of the system or the number of users. So the classical example I've heard that people often use is something called the tragedy of the commons. And the tragedy of the commons is this is a story about a number of people grazing cows on a grass patch. The tragedy of the commons is a tragedy because the more people live in town, the worse it gets. That is, in fact, if there are n people live in town, your welfare or your happiness in the town might go as a function of 1 in n. That is, it gets really, really, really bad. There was a grass patch, it was valuable, you could get something out of it, maybe graze your cows on it. But if 1 million people put their cows on the grass, unfortunately all the cows will starve, and we can't help it. In contrast, here it says, even if you put 1 million people in these actions, you lose maybe 30%, sometimes as much as 50% of the welfare, but you don't lose everything, which is kind of nice, or at least is a positive thing. I can come back in the very end of the talk and mention some results where his numbers go closer to 1, but at the theoretician I'm happy enough that they're small constants of the losses rather than something that grows with the size of the net. So, this is a little bit of like basic of where I'm coming from. Here is the model of what I'm actually using, and this is from a paper of this Todoris Likaris and Vasilis Sirkanis, whose pictures you get to see up there. So here is the concrete mathematical model I want to use for this changing over game. So we're playing the same game over and over again. Every iteration, there are some n players in this game. These are the routers. Every iteration, every player, with some small probability p, and that's going to be a parameter that I really care about, drops out of the game and gets replaced with another player. So in the router context, you should think about it. They're the routers, those are the players. With 1 minus p, a large probability, they're writing a stream of packets. So my packet today is just, this second is just the same as the next second. It's from the same stream. But with a small probability p, that stream ended, and I'm going to start writing a different stream. And then that's a different goal, and it's a different destination. Everything is different about it. And that has a small probability p. I'm going to think of my small probability p as the churn, and I realize how big a churn can I tolerate. The model we're using here is n players, there are p times n players get replaced in expectation. So if I think of the internet, or even the US part of the internet, even though every single router, the probability that the stream ended and the new stream started is a small probability. Of course, overall, in the US, of course, every single second, some stream ended and some other stream started. So there is a significant percentage that did change. Here, every particular player, there's a probability small, but there are n of them. So in expectation, p times n, which will turn out to be much, much bigger, that many players will change.
Does it make sense to consider the same player coming back because they have a memory and history of what happened while they were playing, say, in the first set of rounds?
Sure, could make, like, so, you know, I guess to actually start with, before answering your question, answering the context, I'm kind of assuming that when a player gets replaced, or when a traffic stream gets replaced, you know, it's a new destination, and they're going to have to figure out what they have to do, and not explicitly modeling that if there is a stream going that way, and then I wait a bit, and the stream went this way, and then another stream comes this way, and we'll have some memory. At the moment, we're not explicitly modeling that you might have memory, but I'm also not saying you don't have memory. I'll come back to this when we say what I mean by learning. It's a good question, whether memory could help or could hurt. So what it's trying to do is modeling two things simultaneously. On one hand, even with a small p, and think of p as, you know, roughly, ideally I would like it to be a constant. Unfortunately, we can't quite go up there, so it's 1 in log n is what we will end up being. Still, that's a significant percent. Like, in order to make the change not happen, the probability has to be less than 1 in n. And I feel bad that I didn't push it below 1 in log n. So a lot of people change. So the environment is changeable enough that you need to adjust to the change. You're going to have to watch what's going on. Learning is important. Nash equilibrium in this kind of setup won't work because the environment's not stable enough. But second, I want them, in expectation, most streams or most players stay long enough that they can learn. So this is maybe the moment I should come back to Samir's question. I need it to be the case that 1 in p is a long enough period that in expectation most people learn. So it's okay with me if they're actually smarter and they start from a better start, they still will learn. What's not okay with me, and not okay for this result, if they so set on knowing which way to write, and that turned out to be wrong, that they're not willing to get evicted from that bet. So they should run a learning algorithm that observes the environment and adjusts accordingly, which, given the changing environments, they're going to have to do. it's a trading of two things. They have to stay long enough to be able to learn, but at the same time, be trying to learn to adjust. Okay, so actually, this is the goal. So let me actually start a little bit with, this goal isn't that new in historical context or in the, in world of especially economics and mathematics. So learning in games or learning in repeated games have started in econ in a year before I was born, and I know many of you were born not quite the year I was born. The question that was asked at the time is, maybe learning can help the players find the Nash equilibrium, and the author of that paper is Sarah Robinson, who is a Berkeley faculty member. She used some particular form of learning called fictitious play, don't worry about what it is. Her goal was to help players find the Nash equilibrium. She called this, or people in econ still call this pre-play. That is, they were thinking not of a repeated game that you play repeatedly, but rather a game you play once. And I guess a dominant example of this, especially in the DC area, is the incentive auction that just happened in our US government. I don't know how many of you know about it. The US government wanted to buy back spectrum from TV companies, because before you guys were born, or in fact before I was born, the US government gave away spectrum because they thought that's the only thing it's good for is for TVs, so it gave it to TV companies. But now we realize that no, that's wrong, we need it for our cell phones, so we need to buy it back from them and win an auction. The way they did it, that's a once in a lifetime opportunity to sell or buy auction, sell or buy spectrum. And before they did that, they ran practice runs. What's a practice run? But you know that in whatever, I think March this year, I meant March a year, they're going to run this auction, but you can practice a bit to figure out what might be a good thing to do. This is what she was thinking about. And maybe as you run learning, you go and you find the right equilibrium. And she proved that in two-player zero-sum game, this works. And later on it got proved that 2 players, 2x2 games, that is both you and I have 2 strategies, also works. And that's about the end of it. It doesn't work in any other setting, pretty much. Finding the Nash equilibrium is hard, and actually something that's not on my slides, because, but maybe nice to mention in a CS crowd, because we now know that it's computationally difficult to find. Learning is an algorithm, and therefore this algorithm won't find it because it's computationally hard. What I want to think about is a change of focus. I want to say, I'm not learning to find the Nash equilibrium. I'm just learning because learning is good. And if I do learning, then as I enter the game, maybe I'm one of the players that carry on. I don't know what to do, but hopefully if I'm in the game long enough, I'll get better and will somehow have a better idea of what I can do. And I just want to focus on what happens in a game if they learn. They may not find a Nash equilibrium, I don't care. But maybe something good happens anyhow. This is especially important in changing environment. So, say if the environment wasn't changing, if I go back to Sarah Robinson's goal from the 50s or early 50s, then she was hoping that as they're learning, what will happen is this, that they latch onto a Nash equilibrium, and then from then on, they can just repeat the Nash equilibrium because they learn, they're happy. What does a Nash equilibrium mean? And here's the definition, and we do it in terms of cost. So in the routing game, cost is the time you take, so it's a delay. It's something you want to minimize. And something, a vector a1 up to an is a Nash equilibrium. If your cost, which is cost of player I at this Nash equilibrium A, is no worse than any other action X that you could have taken. If this inequality fails, then you might think X is better. This inequality says that any other X is at least as bad as what you're doing, you might as well stay with your current action. This is a stable solution, a Nash equilibrium. I'm going to call this the no regret inequality. You're not regretting any other action X. So this might be a stable solution, and I guess it would be nice if routing or advertising would be stable in this sense. I do not have traffic routing data, which would be nice to have, but I do have ad auction data. Ad auction data came from Microsoft. This is Bing's like the search engine's adoption, and this is what adoption data looks like. So I picked one particular search word, and this is in days, so I watched for 7 days what are the advertisers bidding on the ads. You can make your own conclusion. I guess one thing we definitely say that for many of these are not stable. They keep changing their bid. If you ask me what the hell they're doing, I think they're running a gradient descent style learning algorithm, increasing their bid and decreasing their bid, and so reacting to certain things. So this is what I would like to know. Yeah.
So what does each color represent?
Sorry, a color is a particular advertiser in a particular keyword. So this all, both pictures are about one particular keyword, and the color is one company advertising. And for those of you who already know about advertising, I made my pictures as friendly as I can. These are very big companies advertising with ginormous budgets, because I'm focusing on what their bid is, and I want them to have that's the only parameter. These are companies that have so big budgets that clearly they're not playing with the budget they're playing with their bid. So I wanted to keep it a single parameter. I'll come back to this data in 1 second. There are companies out there that help them adjust their bids, and I simply see that that's what's happening here. So here is my model of what I mean by learning, and maybe this is a more technical answer to also Samir's question of what do I mean that they're learning. I'm hoping that they copy something of the kind that Nash equilibrium was. So the copied version would be that they do kind of things like they don't have, I don't have a fixed E anymore because over time everyone changes their bid. But if I take this summation here, this is the sum of the costs over time. And I want that to be, or hope that to be, no worse than any single action is hindsight. That is, single acts is hindsight. And of course, I don't quite mean this because, strict inequalities are hard to get to. I allow you a little bit of error as you experiment. So this is called no-regret learning. And what I'm saying, and no-regret was on my Nash equilibrium notion, so here is no-regret learning is the notion of something equilibrium-like without the stability of an equilibrium. So I gave up on stability, but I still want no-regret. No-regret is nice for a bunch of reasons, which I'm going to try to tell you before I tell you what we can do with it. So one reason is that it's doable. I don't know how many of you have seen no-regret algorithms. I hope very many. But they're very simple natural algorithms that achieve this with the regret error. If you do time, t time, and you normalize things so the costs are in 0, 1, just as a normalization, then regret will be at most root t. So with a 0, 1 cost, the worst cost could be proportional to t, and it says, root t says it's low of the time, that it grows less fast than time. Indeed, as time goes on, your error compared to your actual overall cost is less and less. So there are many of these algorithms which I won't elaborate on. So one reason you like it because it's very Nash equilibrium-like and because it's very doable. There are many algorithms that achieve this. This actually has been studied in game theory also. And I guess when people play these learning strategies, again, original hope was that they got to converge to Nash equilibrium, but they won't. But instead I can say the behavior, I can think of that as a probability distribution. It's not, instead of being a probability distribution for each player, it's going to be a probability distribution of these A vectors, that is the collective play we're all playing. And it turns out that converges to something that's called correlated equilibrium. So what's a correlated equilibrium? It's exactly the same thing as a regular Nash equilibrium, satisfying the same inequality, which is now written out in expectation. Every player, what they get, they don't regret any fixed action with hindsight. That was our regret inequality, and I got rid of the error term because I took the limit. But instead of the regular Nash equilibrium, when you and I have to play independently, because that's how Nash works, they're going to get correlated, and in particular, they're going to get correlated because they're all updating based on the past history. We have the shared history we update on, and it serves the signal that we both use and become correlated. Correlated, this notion of learning is no-regret learning is nice in a couple of ways. No need for common prior. You can learn. There are simple algorithms that learn. It's a reasonable behavior assumption because they're algorithms, but it's also, I think, reasonable in just saying it in English. So what I'm asking them to do is that it could be that Tuesday you should advertise different things than Monday. It would be nice if you noticed it. Cool. But if there is one advertisement that you should put up all the time because it's amazing, please wake up to this fact. That's what no regret assumption says. And many simple algorithms. And maybe because I'm a theoretician, it's a model of behavior that I can exploit in proving things about it. It's very Nash equilibrium-like, so I can prove things about it. Again, before I do so, I guess I should actually tell you that there are people who are experimenting, including myself in some papers, in checking whether this is a good assumption as it is true or data. And I guess there are a couple of papers at this point, starting in a 96 paper, that a lab experiment by Aaron and Ross. It's a two-person coordination game lab experiment. A bunch of these papers, actually, over two of these papers are lab experiments. That is, they got people like you in different universities, sit in a lab and try to experiment. I guess one that's maybe following up on us pushing no regret learning was the Nissan and Naughty paper in a year ago, and was making them run auction games in the lab and trying to get them to the players in the lab to bid and see if, do they satisfy this no regret property. The maybe most positive is, or one of the most positive is my paper with Denis Nikitolov and Vasily Sirkanes. We are using this Microsoft data where I already showed you one slide from this. We're using frequent bidder in advertisers where we're trying to find advertisers that are friendly to us as possible. So these are advertisers that changing their bids very frequently, which is they're paying attention to this, and they have very large budgets. And even there, it's sort of an okay assumption, it's not perfect. That is, if you want to look at, so this is the amount of regret they have. Now, one problem is these advertisers, that I have no clue what their value really is. So I see their bid stream, but I don't see what they're thinking in their head. So I have to try to recover from what I see, what value they might have had. So when I say that 30% of the bidders, and these are these guys' value, have literally no regret, that is, these are people who actually have negative regret, they're doing something better, they know Monday is better than Tuesday, or whatever, something of that form. This could be true, could be not true, depending whether I expected the value correctly. Let me say that someone, say up here, has close to 50% regret. That's a fact. Whatever the value is, they have it, that they're not bidding right. So this says that in a positive view, something like 30%, 40-50% of people have 10 to 15% regret, I hope, and the rest of them don't. So some people satisfy this regret condition, some not. It's not a universal condition. If I go back to some of the lab experiments, actually I have a funny disagreement with the Nissan Naughty paper, and their conclusion is that many of the humans didn't satisfy the regret condition, and my conclusion being their data that most people did, especially if their value was high enough. So one funny thing they did in their lab experiment is, say the 5 of you are playing against each other, and they started with value for a bid, 20 cents, 15 cents, 5 cents, 1 cent. So the poor 1 cent guy in the end here, he should just go home. In the proper behavior, he shouldn't win at all. But the guy was made to sit half an hour and practiced this experiment, and apparently those people didn't behave so rationally. I don't know if you would have, sorry. But these people who were given insanely low values, in real life, they should just go home. This auction is not good for them. But in the lab experiment, they were forced to be there, and apparently they didn't behave very rationally.
So in an ad auction setting, probably you need access to the data of the bidder and their website traffic and so on, right? Because that's what they are sort of using as a feedback loop to say, should we raise our bid? If the traffic did go up, then they may have to change their strategy. So unless you have access to the data, it's going to be hard for you to really say what are the thinking.
Yeah, so indeed, I don't have access to the data. I have to, this is a middle week of an ad campaign, not the starting week, so I'm hoping that at this point they have some sense of how valuable it is. Okay, so let's go to, yeah, no more question.
I was wondering, like, why did you mom and based on one social media and you value how they're looking at for an advertiser, there's a pool of search engines. So the opportunity cost of investing in one versus the other should affect using all the others. So,
Right.
do you look at that or
Yeah, so I guess the question is, the simple way that I'm certainly using in this talk is just bidding on one thing, but in reality, you can bid on multiple things, and the trade-off between them is interesting. Definitely, and I guess to sort of answer quickly, which hopefully will make sense to you, and I can do more afterwards. If your alternate options have no explicit complementarities, then everything extends. So if it's never the case that you don't care about the left shoe unless you also win a right shoe, then everything's fine, and it all extends to multiple opportunities. If there are explicit complementarities, then life is hard. So in most of the advertisement case, there isn't usually complementarities between the ads. You don't need this ad to have this other ad pay for it. So usually in ad context, so that condition is satisfied. I'm using the single bid because it is the, okay, I'll come back, I can try to come back at the end of why I'm using the single bid. Learning in a single bid context is easier. I still have the same model, which is on my next slide, that this is what I meant by learning. And if you have so many different options to choose from, achieving this no-regret condition becomes algorithmically much harder. In a single bid case, it's easy. So that's one issue with the multiple bids. So, what I said before and what the classical people use for no-regret learning is this condition. If there are B options, B strategies you're choosing between, then you can achieve in time this root T times log D kind of regret. Actually, what I will use instead is an approximate version, and if you have seen no-regret learning, usually this is the middle of the lecture, they do this approximate version, and then they do something to get the version they like. I like the approximate version better. The approximate version says that if you're within 5% of your true cost, say thinking of epsilon as 5% or 10% even, you're done. You stop experimenting, you're happy. So that says that if I'm willing to tolerate a 10% error, then I can push the regret error, the additive term, down to a constant instead of root T. This will turn out to be much, much friendlier for us in the theory part, and I think it matches the data better. Like there were only 30% of the people with literally no regret, so this seems like a better match to the data.
So all this is for P at most 111.
Yeah. I'll come back to what P was, and actually what I mean by learning that there's P. Okay, so I like this approximate version without adjusting the epsilon for two reasons. I admit it works better for my theory, but also because it matches data better. It doesn't seem like people optimizing all the way to the last cent. Like there's some bigger error that appears to stay. So I promised you to talk about this price of energy, and just as a reminder, this is the Kotsoupias-Papadimitriou definition, the cost of Nash equilibrium divided by the optimal cost. I was talking about learning, so learning actually started with a couple of papers, starting with Avrum Blanc championing the idea, and wanted to look at this version. It says sum of cost over time divided by the optimum. Now, this was a fixed game in which everyone's learning literally exactly the same thing. And so the optimum is not changeable, it's only your strategy is changeable. So if there were t steps, then the denominator is t times the optimum. And what I really want to do is actually not change the optimum also because I changed the players. So exact same ratio, sum of all the costs you're incurring divided by the optimum. But now I have to index my optimum also this time because things change. So this is what I wanted to prove. I wanted to tell you a little bit about this proof technique, which we also using and actually was maybe highlighted in this beautiful paper of Tim Rockgarden, which is 2009, which says that actually a lot of our price of energy proofs are very, very simple, and they like extending to learning. And he called this the smoothness framework. And the one thing I want you to take home from this, that its uses about Nash equilibrium kind of the only thing we really know how to use. That is, if you're a Nash equilibrium, say A is a vector of Nash equilibrium, then no one's regretting what they should have done in the optimum. I want to compare the Nash, what's happening in Nash, to what should have happened, what I want them to do, that is what the socially optimal solution does, and use the one inequality I have about this, that they're not regretting it. Their cost is now no worse than it would have been had they switched the optimum. This inequality then gets added, and as Tim observed, almost all, virtually all, of our price of energy proofs go on the following inequality, which he called the smoothness inequality, comparing the average cost if everyone individually deviates to the optimal solution. So that's on this side. Everyone switches to AI star is what they should have done in the optimal solution, compared to the optimum. What this inequality says in English, maybe that's a better thing to start with, is that if the Nash equilibrium, if the current solution A is very, very, very expensive, it's so expensive that between these two terms on the right-hand side, the cost of A dominates. Despite lambda being above 1, cost of A is so much bigger that dominates. Then one of them can improve the solution by just moving to the optimum. This inequality is really tailored to make Nash equilibrium proofs easy. As we know from the Nash equilibrium, no one's regretting not switching to the optimum, so that gives me an inequality, and then all I have to do is rearrange the terms. And it turns out that for almost all the price of energy proofs, not only that this is our proof, this proof is tight. There are examples that are matching this back, if you play with the longest right. So this proof, as Tim observed, very nicely extends to repeating in the same game. Repeating in the same game would say that, all I need is that I'm not regretting not switching to the optimum using my epsilon version of this, or approximate version of this. It says that if the cost of your solution over time is no worse than if you switch the optimum at every single iteration, that is the single strategy, the hindsight plus regret error, same smoothness inequality, add it up, rearrange the terms, and you get exactly the same thing. What I did here on this last inequality, I actually worked out what happens with the epsilon, and I can admit to you this is why I like the epsilon version. This price of energy proofs usually are giving you a price of energy of 1.3, 1.5, something that's a constant. If you care about a 1.5 price of energy, then 1.5 plus epsilon will be almost as good, and it gives me much faster convergence. So I just worked out what the effect of the price of energy is. Okay. So back to our dynamic here. So far I cheated a bit because I did a detour on the team style, repeating the same game over and over again. And what I really wanted to talk to you about, and I guess I have maybe, 8-9 minutes to tell you about it, is a changing version of this game. So let me remind you what the model was. Everyone wants to learn from past data, but the environment is changeable. Now, there are two parts to this. When the environment is changeable, then maybe they should think about the standard. So what I claimed the standard was single optimal strategy is hindsight. but maybe that's not good enough here. Single strategy is hindsight. Wait. The environment changing, why should I follow a single strategy? That would be down my deep. And if you're not so driven home, then here is an example in routing. You know, this red guy walks in and sees that on this upper route there's an enormous crowd over there. As it turns out, that crowd vanishes and maybe some other guys show up here. You know, hey David, I need to change my route. You have to watch what's going on, otherwise you're not really learning from the environment. So somehow I want a version that works. Now I can also come from the other side. If I want to take the proof I kind of showed to you that is not regretting the optimum is hindsight, then here is what I'm actually hoping. Which is, I want them, which I wish I am, I want them to not regret what the optimum would have done. Okay, that's what I wish I. If I had this, I could just plug it into the proof and I would be all set. I want them to have cost, no worse than had they always done the optimum. Of course, they don't know what the optimum is, so good luck. And what's worse, this is not hopeful. Even if I replace one person at a time, the optimum is an incredibly fragile, changeable object. So just to, in case you weren't convinced, here is the simplest example of the universe. Back home matching, hopefully matching all of you have seen. You know, here is an optimal solution. I don't know, this might be an auction or congestion, whatever it is. One guy goes home, the optimal solution changes by an augmenting pass. Augmenting pass affects everyone, or can affect everyone. So matching is a good example, but this is true on everywhere else. The true optimum is an incredible fragile object, especially if they were close to ties, and then one guy leaves and everything changes. So hoping that they will all actually compare well to the optimum, good luck. The optimum is so fragile that I don't think this is viable. What we propose instead, and again coming back to hopefully maybe some of you have even seen this, that if you go back to the very same learning algorithms that did a single strategy with hindsight, this very same, almost very same algorithm can actually accommodate what they call shifting comparators, a couple of different options with hindsight. So what this version is you want to learn, instead of comparing with a single X with hindsight, I compare to a sequence of X's, which is pretty stable, only K changes in it. Now, if there are going to be K changes, and not too surprisingly, picking up a multiplier K here, and that would be easy to do if I would warn you every time the change occurred, because you just restart your learning algorithm. What's nice about this, that the very same algorithms achieve this without knowing K ahead of time. That is, they can get this band without a pre-warning of what K will be. And definitely no pre-warning of where the changes occur. And just to get a sense that this is actually something that meshes well in what's really happening in real life, is all you have to do to these classical algorithms is this. Put in a bit of recency bias. That is, if the environment is changing, that what you saw today is so much, or yesterday, is so much more relevant than what you saw a month ago. A month ago, that was a long time ago. Let's not take big, like this is why I'm a little afraid of you coming back with a lot of memory. In a changing environment, that's a bit dangerous. And I want to actually recency bias everything, because recent experience is much more relevant than old experience. So once you do this, you get this kind of band. So again, the arrow goes up with the number of changes that happen, but gracefully, and doesn't deteriorate. And at the high level, our theorem says that if people learn with a learning algorithm that this kind of regret error, that is can tolerate changes, gracefully decaying changes, then we recover the price of energy bands almost the same in most games. What do I need to do this? I need one more technical thing, which I probably won't have time to really tell you, but I think I will convince you that thing is viable. I need something that's like an optimal solution, might not be real optimum, but please don't make it so changeable. This augmenting paths, bad idea. Do something different that gives your optimum a stable feature. That is, as I change the population, the optimum should not change much, or at least my part of the optimum should not change much. And if you do this, they can plug this proof in the same, plug this in the same proof system, and you get the price of energy down. So, sort of the summary theorem, which I guess I will maybe have a slide, but I don't know if I have time to show it to you, is one concrete example, is something of the form that an n-size network game is probability roughly in 1 in log n. If they're having this sort of adaptive learning, then I get a price of energy band that combines 3 different terms. There's the old price of energy, which was for Nash equilibrium, that's alpha. There is a little bit of extra error because of the regret. They only in the system for limited time, so they actually didn't run perfectly. It didn't take minutes. And third, I give up an extra factor, which I called here beta, because I'm not comparing to the true optimum, I'm comparing to this approximate optimum that I wanted to get via a more stable solution. So the last technical piece, which I hopefully still have verse listening to, is the stable optimum. So now we are back to classical optimization. There is no games, no nothing. All I want to do is have a solution that's more stable. And to do this, I want to actually have 2 different examples to show you. One gives you an intuition that they should be viable, and the second one gives you a whole literature that other people have been happy with students. So the intuition is coming from matching, which is why I showed you the matching example, and propose that you shouldn't optimize matching so well. How about the greedy matching? The greedy matching is a lot more stable. For example, if I leave the greedy matching, anything that happened in the assignment before I got assigned is not affected, it's greedy. It's not true on autonomic paths, but it's true for this. If you even do the greedy matching with a bit of rounding, that is, not be so sensitive to people's preferences, then you create a lot of ties, and I can tie break in the greedy matching in favor of what happened yesterday, which makes it even more stable. So this is a pretty stable solution. A second, and maybe this is my last technical statement here, there is a whole literature that some of you might know, and unfortunately, due to lack of time, this will be more meaningful for people who do know it, called differential privacy. This is a literature that tries to do optimization using your data while protecting your data. That is, the answer they put out should not depend on your data so heavily. This is especially important if it's medical data or something sensitive about you. Your salary, your medical history, whatnot. And it turns out this is literally the same goal. They want to output something that's not so sensitive to one person being there or not. This is literally what I want. So indeed, we can cash in on a ginormous literature, growing literature of people working out different solutions for different privacy. And one advantage I even have over the differential privacy literature, I don't need an algorithm. This is inside my proof. I just need to know it exists. So I don't need to worry about how fast to compute it. Doesn't matter if you're not planning to compute it. This is all hidden into our proof. Okay, so to end in time, maybe I won't go through this example of the auction, and maybe just want to end with sort of trying to tell you what I hope is the message you got from this. I like learning for many, many reasons, and I guess in particular it's a good way to adapt to the opponent, it's a good way to adapt to changing the environment. It's something that I think is happening in a lot of data sets. But one advantage that I haven't yet mentioned, and I don't have theoretical results to support it, it's a good advantage to adapt to a badly playing opponent. Nash equilibrium, remember in a zero-sum game, rock, paper, scissors, gets you zero pay, in rock, paper, scissors gets you zero payoff no matter what the opponent does. If the opponent's playing badly, then you should get bigger payoff. And as it turns out, all of us are playing badly in rock, paper, scissors. If you don't believe me, there's a very impressive New York Times app which you can Google. It beats me hands down, and I think beats all of you too. Welcome to try it. Send me email if you can beat it. It's an algorithm. And apparently it knows what people do and it beats us. I don't know if it's what's inside is learning, but it does beat us. But I showed in a theoretical sense that learning is also good in a theoretical sense in many games, auctions, and traffic routing may be the dominant example, where if the players are learning, if many or all of them or most of them satisfy this no regret condition, then social welfare is very, very close to the optimal social welfare, which is nice because it's supporting that learning is good for society, not only good for people. And I'm going to stop here. Thank you very much.
So we have time for a quick question or two. So I have a question related to the last thing you mentioned about rock, paper, scissors. How do you know that the app is actually committing to a decision in advance? As soon as you press an option, maybe that's when it decides what to do.
So, for example, I guess people ask me the question of when I said it can beat all of you, which of course I don't know, I don't beat all of you, but I didn't say this almost in my class. Some people in my class tried to practice actually flipping coins. So if you truly randomize, so rock, paper, scissors, what you should do is one set, but it turned out you can't do this in our head. If you cheat, that is actually use a coin, then it doesn't beat us. I trust it, maybe I'm wrong. But one evidence I have that if you flip random coins, it doesn't beat.
There was one quick question.
I'm just wondering, what happens if you have a malevolent player?
Yeah, so that's a good point. Different games are different. In the auction game, the malevolent player can only do so much. And you get a statement on the form that the overall welfare may or may not go to the malevolent guy, but it will be at least as much as the normal players could have achieved without themselves. In traffic routing, it's more problematic because the guy can drive his car in circles in a crazy way and create congestion everywhere. So there are, if you make there are some papers that try to explore this, making some assumption like the graph being a cyclic or some other assumption to limit how much damage a person can do. But clearly, if I can create unlimited congestion and it doesn't hurt me because my objective is different, I can ruin the traffic. So that's bad.
Okay,